Thank you, Janos, for the introduction. And thank you very much to all organizers for inviting me to give this talk. So this talk is written algebra versus logic, but it should be algebra and logic, and they are not fighting, but having a beer together. And I will follow. This talk follows somehow the track of some track of research that stemmed from language theory and the notion of regular languages, and with two point of views: one from the ones from algebraists and the one from logicians. And I am trying to explain how some interactions happened and how they fit well together. So we start with finite words, and we go toward infinite words. So that was a mandatory subject here. Okay, so now I need to click here. Our basic object will be finite words. And so if we see, as a computer scientist, a finite word is just a finite sequence of letters, symbols from a finite alphabet. So no need to tell you more about that. I just give some randomly chosen examples. And all the story here is about how can we define properties of words, which is equivalent to say how can we define languages, so sets of words over a fixed alphabet. So, as you know, there is a long history of, do you see? You see here, there are tracks that are colored. So there is a long history since the beginning with Turing, who's hidden up there with general Turing machines, the first neural networks. Von Neumann, I learned, coined the term automata theory. All this, I've just taken it from a survey of Dominique Pera, which is very nice, but in French. But I discovered a lot of things. So you have this famous result of Kleene, expressing the equivalence between the rational expressions and automata. And at some point here, you get to have this work of Schützenberger, which is the origin of the left branch. And Schützenberger says, if you are a regular language of finite words, it's the same to be recognized by a semi-group or a monoid, and even there is a minimal one, which is called the syntactic monoid. So this is the starting point of the algebraic branch. And then stories goes on. People discover non-deterministic automata. There is this notion of congruence. There is this famous paper of Rabin and Scott, who gave them the Turing Award. And at some point in the 60s, three logicians, so Büchi, Elgot, and Trachtenbrot, show the decidability of weak monadic second-order logic. So I will say, for simplicity later, monadic second-order logic over finite words, but that's essentially the same thing. Then Büchi gave the fundamental contribution of going to the omega, and then there was a continuation, and this I will call the Logician branch of research. And I will try in this talk to see how there are interactions between these two sides. Okay, so we start with the algebraist point of view. So if you ask someone doing algebra, what is a word? The answer will be, but it's an element of the free semigroup or the free monoid. Well, it's not completely true. You could also say it's an element of the freely generated algebra over right actions, with finitely many right actions. That would be also other possibilities, but that's the most common one. So let me just recall what is a monoid. A monoid is just a set, equipped with an associative operation and with a unit element, one, and the semigroup is the same thing without unit. So when you're doing, when you're working in this area, you jump from monoid to semi-group depending on the context. They are almost the same, but inside proof, sometimes you prefer one over the other. So I could interchangeably use one or the other. So the first example of the free monoid is, of course, the free monoid, consisting of all words over the alphabet sigma of the concatenation operation or append operation, and the empty word as a unit. But you have other examples. So typically groups are special cases of monoids. Yeah. But you have also other ones. That's why I wanted to click on this cross. You have other ones that do not look at all like groups. So for instance, the maximum over a sequence of numbers, there is no way you can invert an operation. And of course, you can build a lot of them. So here is an example of a finite monoid. And you can check that the operation of product is associative. Good luck. No, it's easy. But uninteresting. So starting from that, what should be a language? A language, it's so it's a set of words. So it's a subset of the free see, it's the same. It's a subset of the free monoid. But another way to say it, it's a map from the free monoid to 0, 1. It's not a morphism, it does not respect any structure, it's just you send some words to the value 0, which means outside of the language, and some words to the value 1, which means inside the language. And from that, there is this notion, so I guess Schützenberger should be considered as the guy who introduced it, which is the notion of being recognizable. So you care about a language. Don't know how it works. Yeah, no, like that. Yeah. You care about a language L, so a map from words to 0, 1, and you'd like to describe it. And the way you do it is that you give a morphism. So you send every word to an element of a monoid M. Okay. And then you have a final map that sends every element of M to either 0 or 1, accept or reject. Okay, and so the thing is that in this morphism, because you have to preserve the structure, it means that whenever you have your morphism has computed some information about words and you concatenate them, then the information about the resulting word should be the product in the monoid. So in some sense, this morphism contains all the propagation of information that is necessary for recognizing the word. And also, I mean, this notion is, of course, something interesting for a computer scientist, because you can encode a morphism by just giving the image of the letters. Okay, so typically this is how you can see it. You have your set of words, you send them by morphism to some monoid M. So in general, it does not cover the whole monoid. And then there is this monoid is split into two pieces, the one that are sent to 0 or 1, the one that are accepted and rejected. Typical example, so if you want to count the words that have lengths 2, that have of even length, then you would use the Z over 2Z monoid. So it's a group, but you can forget about invert, it's a monoid. Your morphism would be the length modulo 2. And you just send the even part of Z over 2Z to 0, the odd part to 1, and you accept if the value is 1. So, yeah. And so technically what it says here is just if you have a word of even size and you concatenate a word of even size, it's even size. Odd size gives even size, and so on. You may have also the same technique works for more complicated languages. So for instance, if you want to check whether there are as many A's as B's, you would send the words over A, B to Z, and your morphism will be the number of A's minus the number of B's, and then you check whether the result is 0 for outputting accept or reject. And if you use this table, which is here, it's supposed to do detecting whether the factor AA occurs somewhere. So it has been constructed, well, you don't care. So the key result here is that this notion of recognition corresponds to the notion of regularity, which was introduced before, using, for instance, automata. So I don't want to introduce automata at all in this talk, but I can just phrase it in 1 second. If you have an automaton and you look at a word, you can gather all the information about the possible transitions. For instance, there is a run from state P to state Q over this word. And once you have gathered all this information, this is one element in the monoid. And if you check, it's compatible with product. So this will be a morphism that will recognize the language. And the other way is even easier, because if you take a monoid and you just look at the effect of making the product with single letters, with the image of single letters, it's just a deterministic automaton. So you just throw away some information and you just have it directly. So once you have given this definition, then you can use first some general facts for people doing algebra, which is to use a bit of extremely low universal algebra. So it is in universal algebra in the sense that what I'm saying here is independent of the fact that it is product or the fact that there is associativity. It could be for any kind of algebras. So the first thing is that if you have a morphism from an algebra to another, then you can restrict the second algebra to the image of the first one, and the result will again be equipped of an algebraic of the structure of the same algebra. And then other is if you take an algebra and you give an equivalence relation on it, which needs not to be compatible with the operation, then there exists a closest congruence that refines this equivalence. And when you use that, you get as a corollary that when you are given a language L, then there is a monoid that recognizes it, and which is furthermore minimal for division. So in the finite, this is like minimal in the number of states, but it's a strong minimality in algebraic sense. So division means it's a quotient of a subobject. But how does it work? It works that you take the set of words equipped with product, and you quotient, and you say, oh, but it's naturally split into two pieces, two equivalence classes, things that are inside the language, things that are outside the language. So I can fire this theorem here, and then I can just quotient it. And now, so the other theorem, I will not do it, but it's to prove that it's minimal for division. So you should imagine that you have another monoid that would recognize the same language. Then you would discover that it induces some congruence on the set of words. But this congruence here is the minimal one that, and this congruence has to be coarser, has to refine the equivalence relation of the language. So because this one is the coarsest, it has to be finer than it, and so on and so on. And then you pack all this together, and you get that it is minimal. So what I want to say here also is that all this is absolutely irrelated to the fact that we are talking about words. I would just mention one thing, is that this theorem of congruence expects that the algebra that you are considering are finitary, so which means that you have only operations with finitely many arguments. You may have infinitely many operations, but each of them has only finitely many arguments. Okay, so that's the limitation. Okay, so far it's very generic. We did not say anything very strong, and so the real first insight in this story is this result of Schützenberger. And Schützenberger was considering what are called Starfree expressions, which are like a variation of the classical regular expressions. So what you have here is you construct languages using a few atomic constructs. So you have the empty language, okay? you have the language consisting only of the empty word. Okay? And you have languages consisting of one word with one letter. And then you can make union, intersection, and complement. Okay, and so if you think about it, if you have such star-free expressions, then, so it's star-free because you don't have the cleany star. But in exchange, you have complement, which you usually don't have in Russian. Yes, of course you have concatenation. Sorry. With concatenation, that is clearly missing. So, finite languages, you just can construct any word by either saying it's the empty word or concatenating letters. Then you can build finite languages by making finite unions. Easy. Then the full language is, you can see it as the complement of the empty language. So as a consequence, for instance, you can say if you have a word u, those words that contains the word u as a factor, how do you do it? You say, oh, but these are words that start with sigma star, concatenated with u, which we have seen could be expressible, and then concatenated with the full language. So this is having a factor. You can also say having a given prefix or a given suffix with variation of that. And so from that, you can, for instance, express the language A, B star. You say, oh, I have only A's and B's. I don't have the factor AA. I don't have the factor BB. I want to start with an A. I want to end with a B. So it's a conjunction of several things, like an intersection of several things. And this is the language A, B star. And so, but if you think about it, there is no way you can somehow count modulo something, and so you can formalize it by making, say, a proof by induction that shows that the words of even length, so AA star, cannot be represented by any star-free expressions. So what is the extremely famous and like subtle result of Schützenberger? It is that you can, in fact, describe the languages that are expressible by a star-free expression exactly as the ones such that their syntactic monoids, so the minimal recognizer for them, is, so first, finite. I mean, we are all in the realm of regular languages, so it's finite. And aperiodic. And what does aperiodic mean? Okay, to make it short, if you are in a monoid and you can start to iterate an element, so a square, a third, and so on. If your monoid is finite, after some point, you will have to fall again on a given point. But in general, this can be loops, like z over 3z. You may have a square, and it's only after finitely many steps that you come back. In aperiodic monoid, all the elements are ultimately constant. So when you iterate elements, after some point, it does not change. So if you think, I mean, can I do the proof here? It's the same as saying that nowhere inside the monoid there is a group. So here we have to be a bit cautious because using a group, meaning, a group is like a monoid, but it has an extra operation of inverse. And here clearly you don't have an inverse operation. So what it means is that there is no subset of the monoid such that would have more than one element, so it's non-trivial, and that you could equip with an inverse operation. Okay, so it's group trivial. But you see here, or you should have the intuition that if you have a monoid that accepts this language AA star, it has to somehow count modulo 2. And concretely, this means that somewhere hidden in the structure of any monoid that would recognize the language, you will find the group z over 2z. And that's exactly what this result of Schützenberger is saying. It's saying, if you have a language, either you can express it as a star-free expression, or all monoids that recognize them contain a group. And in particular, the minimal one, which gives a decision procedure, because this one you can compute and check for this one. Okay, this result is often combined with the result of McNaughton-Papert, which was a few years later. And because this class is equivalent to first-order logic, I will tell more about it in a few minutes on the logician side, and to counter-free automata. Okay, and this first result was the origin point of a long line of researches with many other families different from Starfree expression, like piecewise testable languages, locally testable, I don't know. So even the first order hierarchy, you can try to decide its first level, which you could say is the number of negations that you use in a formula in a nested way. You can have separation results, like given two regular language, can you find a Starfree definable language that would be larger than the first one and not intersecting the other. All this, there are all these results, and they all rely on the fact that when you have this algebraic object and you look carefully at its structure, you can know a lot of things about what is expressed by the language. So this original insight of Schutzenberger. And here, when you are doing that, the way you do it, the way you think about it, is that you have a clear understanding of what is a clear, a non-trivial understanding of what is the structure of monoids, and in particular of finite monoids. And here, a key tool are what we call Green's relations. So in 51, Green studied the ideal structure of monoids. And so it looks like ideals, but there are subtleties because your product operation is not commutative in general. So you have left ideal, right ideal. LNR relations are related to that. You may have ideals both left and right, and you have like several things like that. And in the case of finite monoids, they behave particularly well. And so the result is that when someone works in this field and you tell him, oh, look at this monoid, you will never draw that nobody can understand, but you will draw something like that. There is one J class of the unit element, and then there are 4 H class arranged, and so on and so on. And this gives a lot of intuition about what's going on. And that's, yeah. And this view has other consequences. There is this famous result of Krohn-Rhodes, which essentially says if you have some regular computation, you can describe it as a cascade of simpler ones. And another one that I like is this Simon factorization Forest theorem, which essentially says the following thing. If you have a very long, a sequence of elements in a monoid or a semigroup, okay, and a priori, if you want to evaluate it, you have to read them one after the other. But this factorization theorem tells you that you can decompose it. So you have your long word, and you can find, for instance, sequences like that, such that if you evaluate the factor, they will, for instance, be always the same idempotent. So it's like a Ramsayan decomposition. And you do it, so this will give you a new node in your tree. And then you have a decomposition. I don't know if my picture is clear, but so you have a decomposition of your long product into a bounded number of steps. But these steps are repetition of the same element. And this is a very nice result when you want to exhibit a lot of regularity on an input. Okay, so now the other side of the story. So what we have discovered here, so what I've explained here is that if you see from the eye of an algebraist, then you understand a lot of things about the structure, what are inside languages by looking at the minimal algebra that recognize them. But there is another point of view, which is the one of logician, if you ask a logician what is a finite sequence of letters, he will say, oh, but that's a model. So what is it? It should be a labeled chain. So let's say a total order on positions with extra predicates to say where are the letters. So maybe you can, so that's what they call, is called labeled chain. So you have one binary symbol that is interpreted as a finite linear order. And you have unary predicates. So unary predicates holds on each position. And when you see a model here, so I did not draw the total linear order, I just draw the successor. But you can say the first point satisfies P and Q, the second P and not Q, and so on. And the linear order gives a structure and give the sequence of elements. And you can see it as a word over the alphabet 2 to the number of predicates. Okay? So it's a bit painful to jump from sigma to 2 to the k, depending on the context. So you can also do it the other way. So if you have a word over sigma, you can always see it as a total linear order, but with one unary predicate, one monadic predicate for each letter of sigma, but you require that they form a partition because you want exactly one letter on each position. So you always have to jump between these two things depending on you want to be on the logic or the algebra side. But this is, okay, not a problem. And so sometimes I will use the term generalized words as words that corresponds to labeled chain. So words that I do not require to be finite. So they are infinite linear orderings, and on each of the positions I put the letter. Okay. So now if you ask a logician how you could classify your inputs, then the answer is, of course, give me a logic. And the first answer is, of course, give me first order logic. So first order logic, you know it. So just to get warm on this subject, first, the fact of being a linear order, so a total order, is something that you can express by a first order formula. In first order logic, you can define the notion of a successor. So y is a successor of x if y is after x, and there is no point that is in between. Okay? You can, of course, say my chain has a first and a last element. You can express things like being dense. So whenever I have 2 points, I have one which is in between. And you can say, so what I wrote like being a pseudo-finite linear order. And so what is it pseudo-finite? It's because it's from the point of view of first order logic is indistinguishable from finite linear orders. And what does it mean? It means you have a minimal and a maximal element. And for all element that is not the maximal one, you should have a successor. And for all element that is not the minimal one, you should have a predecessor. So of course, this is something that is included, that contains all linear orders. But it also contains things that are non-linear orders, like so that's a very simple example. Is this one. So you put here a copy of omega, seen as a linear order, and then a copy of the reverse of omega, which is traditionally written omega star. And the fact is that, well, it is pseudo-finite, it is not finite. And okay, if you know a bit the theory and what's going to happen after, in fact, first order is unable to detect this kind of behavior. So it's undistinguishable from a finite linear orders.
Why did you say that this is not a linear order?
See, the finite is the thing I'm...
You said it's not a linear order.
I said it's not finite. Well, no, I said it. I wrongly said maybe it was a... It's not, of course, it's a linear order, but it's not finite is what I wanted to be. Yeah, sorry. Thank you. Okay, but you cannot express the order is finite, and for this, typical tool of a logician would be to use compactness, because in first order logic you can say I have at least size n. Okay, and imagine you would have a formula that say I am finite. Then you would say you could say I am finite and I have at least size 0, at least size 1, up to size n, and this you would have a model. So using compactness, you would have a model of your formula that says I am finite, but also the conjunction of all the formula that says I have at least size n. So of course this is a contradiction. And which is maybe not, well, I've never seen this very simple argument, but you can also deduce, for instance, that among the finite linear orders which you can express, you cannot express in first order logic that you are of even size. So usually it's done using Ehrenfeucht-Fressé, but in fact you can see it as a consequence of this, because you could say something like, I am pseudo-finite, which you can do. I'm assuming that I have a formula that says that I have, that separates inside finite linear orders the ones that are finite from the ones that are not finite. I call it, the ones that have even size from the ones that have odd size. Let's call it even. And I can write the formula, I am pseudo-finite. I look like I have an even size. And if I remove the first element, I don't look like I have an even size. Okay? And so the thing is that if you believe that this is even, okay, then because it's isomorphic, you should also believe that this is even. So that's what you say. You say, okay, you believe that it is even, but if you remove the first element, you should not believe anymore that it is even. And you can check that over pseudo-finite words, this kills all infinite linear orders. Okay. I just thought it was a funny, non-classical pass in the proof. Okay, but in this specific context, there is a key logic, which is monadic second order logic, which happens to have plenty of good properties. But let's first say what it is. So it is the extension of first order logic with set quantifiers, because monadic means monadic predicates means predicates that have just one arity 1, so which means that hold on a given position, so we can understand them as sets. So we can quantify over sets, and of course we have all first order, and we can say a first order element belongs to a set. So now this logic is strictly more expressive. So for instance, you can express reachability by saying that all, so imagine you here we are outside of linear order for 1 second. Imagine you just have a directed graph, 2 points x and y, and you want to say that there is a path from x to y. Then what you say is all sets that contains x, so contains the source point, and that are closed under the edge relation, which you can express also, should also contain y. Okay? As a consequence, you can express the fact that you are a finite linear order, because you say, oh, I have a first element, a last element, and I should be able to reach the last element by applying reachability on the successor relation. And you can also say you are, for instance, of even length, because you can say I can reach the last elements by steps of 2, for instance, by double successor. So all this is related. So the key insight here is that is this result, which has been stated 3 times independently by Buchy, Elgot, and Trachtenbrot, which is that MSO is equivalent over finite chains to regular languages. It was not phrased like that. It was weak MSO over omega, but for here it's perfect to say that. And here, in fact, in MSO, you can think about the capability using your set quantifier to guess runs of automata. So that's why MSO naturally captures non-deterministic automata. Conversely, if you prove, yes, so you can prove if you know that the regular languages are closed under sufficiently many operations, then you can simulate all of the construct of your the logic, and so you can make the other translation. Okay, but now, for a logician, being finite is something not funny at all. I guess it comes from the origin of the topic. So the real insight is when you go to infinite, and this is this result of Bucci, which says that monadic second order logic is equivalent over generalized world of length omega to some suitable form of automata. And it is a non-trivial result. And it has consequences. All the things I'm describing are effective, so it has consequence of decidability. So for instance, if you give me a monadic second order formula and you ask me whether it is true or false on omega, it is decidable. So your model looks like that. No, but this one is 62. Now, the key, one of the main results in this topic is this result of Michael Rabin, which is that you can go beyond omega and go to what we now call binary tree. It was called S2S at that time, the logic S2S. But you can see it as this structure where you can go to the left with a special relation and go to the right with a special relation. So if you just look at the left branch of zeros, it's omega, but it's branching a lot. And this theory is much, much, much more complicated and interesting than the one of omega. And in fact, it's somehow, there are few possible extensions of that. So this result is a masterpiece of in this branch. So some people call it the mother of all decidability results. Okay, maybe we should relativize it to maybe in verification, or I don't know, or in automata theory, I don't know. And Moshe Vardi, for describing all the theory that was behind that, the equivalence between logic and automata and the games involved, all these very nice things, describe it as a match made in heaven, as a paper with this title, I think. So, but here in our case, let's look a bit more precisely. What can you express on this infinite binary tree? So the first thing is that, okay, we are in monadic second order logic, so we can express reachability, so the existence of path. So as a consequence, you can express the ancestor relation in this tree. You can say this node is below this one. And you can also express, as a consequence, the infix lexicographic ordering. So I did not have space to do it, but the idea is when you want to order your tree, you can say that all the nodes that are below to the left are before this one, and all the nodes that are on the right subtree are after this one. So essentially, if you look at it on a finite tree, this is like the normal depth first search from left to right, but where the point is in the middle. The node is seen in the middle. And if you think about, so first it's definable in first order logic, and if you think about it, this is a linear order here that has the property that it is dense. So you can check that this linear order, whenever you have two nodes, you can find another one which is in between. Okay, it is dense. It has no minimal point because you have an infinite descending chain of nodes on the left branch. It has no maximal point because you have an infinite ascending chain of nodes on the right branch. It is countable because there are countably many nodes in the infinite binary tree. So as a consequence, it is isomorphic to the rational line. So this formula here is in fact interpreting the rational line. So let's write it like this. Inside the infinite binary tree. So as a consequence, the monadic second order theory of the rational line is decidable by an embedding inside the infinite binary tree. Okay, let me just mention that once you know this, in fact, you know more, because a formula of monadic second-order logic can quantify over sets. So you could, since you can embed any countable linear ordering inside the rationals, you can deduce from that the theory of all countable linear ordering is decidable. You just write a formula that first guess the subset of the rational and then express the formula you care about on it. And in the same way, here we are talking about linear orders, but it could be words because a formula can also guess the labeling by letters of each positions. So that's one power of monadic second-order logic, is that you can like guess subset and guess labeling. So a lot of problems turn out to be equivalent. What time is it? Oh, but I'm late. No?
No, you started 5 minutes later, but you had a call.
Okay. So the next step in this story was why do you say 76? It's 75. It's a result of Sheila. So this result of Sheila it has two parts. One is a new proof of decidability of monadic second-order logic over the rational line, which was known by Sheila, by Rabin. And the other is the fact that if you go beyond the rational line, if you want to apply monadic second-order logic on the real line, it is undecidable. So the first proof was under the continuum hypothesis, and then this was removed, and there are variations around this. Here, Sheila is using completely different techniques. So what he's first, okay, let me just try to sketch a bit some things. So you have the language of you have first just an order here. So you can consider the set of formulas up to quantifier rank k. And the thing is that if you rewrite these formulas using elementary things like De Morgan laws and things like that, it turns out that there are only finitely many of them. Okay? It's obvious in the sense that deciding the equivalence between two MSO-K formula is a priori not decidable. We don't know. But here this argument is completely effective because you just use elementary rewriting between formula. And now if you give me a sequence, a linear order, you can define its K type. So it should be the 0 type in the normal logic terminology, but it's the set of sentences that of quantifier rank up to k that all holds on U. And the key argument in Sheila's proof is that is referred to as the composition theorem. It says that if you have a linear order and you have chopped it into pieces that are convex, then you could look at the type of each of the blocks. Okay, and in fact, the type of the original sequence can be in fact recovered from a kind of multiplication just on the types. Okay, so you don't need to know exactly what is the content of this. You just need what are the formula that are true here, and you need to know how are organized the pieces together along a line, and that's sufficient for having the type of the result. And and multiply is some map that exists. Here we don't really care. Of course, this does not give the decision, but procedure. But the intuition is that this operation multiply is infinite in nature, but you can restrict it to just a few operations, which are what is the effect of concatenating two sequences, what is the effect of making the omega iteration, so repeating omega time the same sequence, omega star time, and there is also a shuffle, which I don't have time to discuss here. And there is an argument by induction on K for being able to compute that. Yeah, and then this result with Yuri Gurevich, they removed the continuum hypothesis and they went beyond the rational line, but for P modest chains. Well, I'm not exactly sure what it is. Okay, so from the point of view of the logician, we should not be afraid to go to the infinite. And well, there are techniques for deciding things. Of course, how do they, what is the interplay from the point of view of the algebra branch? So here, probably I will not cite everyone, but there is this book of Pin and Pera, who defined the concept of an omega semigroup. And an omega semigroup, it consists of two sorts. One corresponds to the sort of finite non-empty worlds. The other corresponds to the sort of infinite worlds. And there is a product. And this product says, okay, if you concatenate a certain number of non-empty finite worlds, you get to have a finite world. If you make a concatenation of omega length of finite worlds, you will get an infinite word. And if you make a concatenation of finitely many finite words, then an infinite word, it should be an infinite word. And it should satisfy suitable identities. In fact, if you come back here, this picture here is exactly like that. So you can see here, this is the product of the elements which are the types on each position. And the associativity rules essentially say, if you would have chopped it into different pieces, you should still get the same result. Okay, so typically, if you look at the types up to quantifier rank k and the multiply operation, this is something of this form that goes even beyond length omega. So here I should say two things. First, it is an infinitary algebra because now this operation, it maps infinite sequences of elements to elements. So the generic things that I've said about using universal algebra in this context do not hold. So you don't have in general a syntactic algebra. But the interesting thing is that if you know that what you are representing is recognizable by a finite algebra, then you will recover the fact that there is a syntactic one. A kind of magic. You trade the infiniteness of the algebra and the finiteness, the finitarity of the algebra for the finiteness of the algebra, but you have infinitary operations. So these things arise in a very general fashion because you can see them as Eilenberg-Moore algebras in suitable monads. So this is something that Mikołaj has developed and which is quite used in many other contexts now. But as you see, again, we fall on the same problem that this operation is not something that you can compute with because it's an infinitary operation. So here there is this key insight of Thomas Wilke, who says, oh, but you just care to use the product between finite worlds, the product of a finite world with an infinite world, and a single omega operation that simulate the effect of iterating always the same element. And then you have new, so you have some associativity rules that are obvious, but you have new identities that say if you repeat a word n time and the result omega time, this is as iterating it omega time. And another one that says if you alternate uv, 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 you can either parenthesize it as uv to the omega or as u concatenated with vu to the omega. And what says Thomas Wilke is that these two notions are equivalent if the carrier sets are finite. So it's the same to give these two operations or to give this infinitary one. And this approach gives rise to being computable. So this is what we call Wilke algebra. But if you have in mind what I told about Sheila's proof, he had this composition theorem, but then he had these things that he was using only omega, omega star, shuffle, and product things that he had to compute inductively on K. So there was the same flavor there. So what we have here is that now the algebraic point of view is able to capture infinite linear orders or infinite objects. So here, this is something we've done with Olivier Carton and Gabriele Poupis. So we've somehow extended the approach of Pin and Pera and make it match with the paper of Sheila. So, so we have a notion of algebras, but with operation omega, omega star, and shuffle, and we give the axiomatization for it. And we prove that being recognizable by an algebra is a property of countable worlds that is the same as being MSO definable.
So what do you mean by finite countable? I think there's some typo.
Yeah. It's an algebra for countable worlds. So it has, so you're right, it's perfect. It has, okay. But the sets on which this operation act is finite. Okay, so, so yeah, you're right. It's, okay. Sorry. And it's the same as being MSO definable. So one direction is like going from a monadic second order logic to being recognizable, which means constructing this table of specific operation, and then there you just can follow the same track as Sheila. Maybe you present it differently, or but essentially that's the same spirit. But in Sheila's, paper, there is no way to come back to MSO. And in fact, coming back to MSO is absolutely non-trivial. Because you cannot do like on finite worlds where you would just go from left to right and pass the whole thing, because you don't have an induction argument on the chains that look like the rationals. And so here we use extension of this factorization forest theorem, which, so I remind you it was like that, which has been extended to infinite linear orders. And so it gives you an induction parameter for constructing your MSO formula. So your MSO formula will first identify factors of a given form. It's not, okay, no, it's not working like that. In fact, your formula will guess a decomposition of the input word that would be a witness that it should be evaluated in some way, and then it's checking that it is consistent. And this point of view was absolutely not available without the algebra perspective. So that's where the two things work very nicely together. And so from the fact that we could recover this back arrow, there was three open problems that were immediately solved. One was, you know that on finite worlds or even on omega, monadic second order logic collapses to one existential quantifier. This is not true for the rational line, for countable linear orders, but you just need one alternation of set quantifiers. And so, so this is the result, and it comes from the fact that you pick a monadic second order formula, you send it to the algebraic world, and then you use this factorization forest result to come back, and then you have one alternation of quantifier because you need to guess the tree decomposition of your input. That's one exist quantifier. And then you need to check that it is correct with respect to dense things and so on. And there you need to use a universal quantifier. And all the rest is first order. The second was a question that was raised by Gurevich and Rabinovich. And it's like that. You have a property over a set of rational numbers that you express. So you have a set of rational numbers. And you have a monadic second order formula that expresses a property over it. But this formula can even talk about the reals, so about the Dedekind cuts that could be there. Can you express the same properties? And the answer is yes. But as you know, the real line has an undecidable monadic second order theory. So the answer is yes, but it's absolutely not effective. And another one is, well, if you describe a language as constructing a regular language of infinite trees that may have leaves, and you look at words that you can write on the leaves, and you assume that two words that have the same word on their leaves either accept both of them, either both are accepted or none, then the language of leaves, of yield, the yield of these trees is also regular. It was also an open question, but maybe more maybe more technical. And then we went on like following the same path as Schützenberger has initiated, but now for these very long words of countable length. And the first result was with Srijit. And we characterize what it is to be first order, what it is to be, and okay, a sequence of other logics. So because you can also be first order with access to Dedekind cuts. I'm almost finished. And so you get to be able to decide whether a monadic second order logic is equivalent to a first order one over countable linear ordering. And the way you do it is you construct the algebraic object and you just check some algebraic properties on them. And so one which is used for first order, one among others, is this one that you have u omega times u omega star is equal to u, let's say, repeated, okay. When you iterate an element, after some point, because it's a finite algebra, you come to a group, a cyclic group, and there is an idempotent there. This is what you call u ident. Usually it's called u omega, but it's very ambiguous in this context. And then essentially this means a word that is sufficiently long. And this identity says, oh, if you insert a gap like that, it is not possible to separate it from a sufficiently long word. So this identity is precisely putting in symbols the intuition that you have that first order is unable to detect gaps in your linear orders. And you have a list of such properties, and like that you can characterize other logic, what it is to be weak MSO, so quantifiers over finite sets and so on. And we continued with, so Remy and Sam are here. What we've done is extend, well, for the moment partially, extending separation results over infinite linear orders. So if you give me two MSO formula that talks about a generalized word of ordinal length, are you able to find a first order formula that is larger than the first one and excludes the other? So it's an extension of classical results over finite words. And more recently, with Alexander Rabinovich, we used also this technique for solving open problems in for logicians. Well, these one were somehow motivated from the results before, but this one was really motivated by what logicians were asking, which is if you have an MSO formula that is true for some set, are you able to construct a set that is the witness of why it is true? For all words, for finite words, it's easy. You just have to pick the lexicographic list one. You can make this word for all ordinal that are smaller than omega to the omega, and it's known to be not true beyond that. And so among other results, we are able to decide, given an MSO formula, whether it can be uniformized over words of ordinal countable length for the moment. No, but that's my conclusion. Thank you. No, that's not bad. I was talking I was talking because I was saying 3 minutes. No, I'm good on time. That's just what I'm saying. So, well, the conclusion is, but it will be very short. The conclusion is that there is a nice interaction between this algebraic and logical side, and the theory is somehow unified. You even understand better what's happening on finite words once you know that. And this helps resolving problems, say from logicians by algebraic techniques, but there are also other relations that in the other way that I did not mention. So what next is the question. So I wanted to end with some open problems. And if I would name two of them now, one is we don't know the equivalent of Wilke algebra for infinite trees. And it's a complicated problem. I cannot explain all the details here, but the fact that constructing trees that are infinite requires to have plenty of dangling branches, and you should name them to put substitution in the proper one, means that these are algebras that are infinitely sorted depending on the number of variables. And so this introduces plenty of problems. And another one, which was asked by Sheila, I think in the first paper, is, okay, you know that the real line has an undecidable monadic second-order theory, but what happens if you restrict your quantifiers to Borel sets? So it is known that if you restrict it to open sets, it's decidable. It just reduces to things that are known. But for Borel sets, it's a completely open problem. But I guess it requires to know a bit of descriptive set theory, or yeah. Okay, and that's well, that's all I wanted to say. Thank you.
Thank you very much for the nice talk. Now, first, do we have open questions? No. Any questions?
Thanks, Thomas. This was really great. I want to know if people looked at other shapes of orders, but linear orders, words over linear orders. Then you have words over trees, and there are many things that can be stated. But how about you take a well quasi-order? So this is an interesting object. Has it been looked at from this point on view?
So the thing is, here there is one central point is this logic monadic second order logic, and you see that if you can guess coloring of things, if you have a grid, you can guess a run of a Turing machine, for instance. You can say each row is a tape, and the different rows means the advance of time, and it's very easy to check a run of the Turing machine, so it turns out to be undecidable very easily. And in fact, as soon as you have a grid-like structure, like even a minor, no, let's say, that's not completely true, but okay, let's put it like this. As soon as you can define in some way something that would look like a grid, there would be problems. So as soon as you want to go to things that are okay, and by what's this? This minor theory, excluding a grid, at least for structures that don't have too many relations, this is as being of bounded tree width. So in some sense, there is a limitation here that you should not depart too much from the trees. So you can go to trees of a given tree width, like Courcelles theorem is a version of it for finite words. But beyond that, there is a few hope. And so, of course, there are studies, but it's with different logic and completely different techniques. So you have results like you can efficiently decide a first-order property as soon as you, for instance, locally exclude a minor. I mean, but I'm not an expert of that. You have several experts of this kind of question. But it's a completely different branch because, well, you change of logic and you, of course, have to completely change of techniques.
Any more comments, questions? Yes?
So Q is like the general linear countable order. And what would be a tree equivalent to that? And
to the rational line?
Yeah.
Okay, so you okay.
Could it be?
No, so you can go beyond. So for an order to look like a tree, does not require to say that the branch have length omega. So you can say, oh, it's a linear order such that all upset, say there is a root and all upset are totally ordered. And you can go a bit further in this direction, but this is done by somehow interpreting it inside the Rabin's result. So it does not require to develop new tool, and there is no, well, that would require a longer response.
It's not easier than studying the infinite binary tree.
No, it's more complicated. It's more complicated because you can say I am a tree and all my branch have order type omega. So
what
you
I'm
can.
saying is it's as hard as.
Yeah, it's essentially as hard. Yes.
Thanks.
Any more? So let's thank the speaker again.